this will help you to solve many numericals. I do. So some of you are asking, sir, interference. Still, many problems are there I to cover. Let me just finish off all the syllabus first, like closed-end organ pipe is there. Next beats, Doppler effect. Then together all at a stretch. Once I finish off beats, no, together what happened? Or organ pipe, I'll finish off. Organ pipe intensity combined, I can do many problems. Many interrelated problems are there. Then I'll go for beats and Doppler effect. The interference, some 10 numericals is what still I have to discuss, not 1, 2. Resonant frequency of closed-end organ pipe. So I have a organ pipe. What are its resonant frequencies? So let L be the length of the pipe. So there's a tuning fork. So it will start vibrating. So as it starts vibrating, so it will push the air beside it. So now when the incident wave will go like this. So here first the incident wave. Let me call Y1. It will go like this here. This wave will arrive here. By the time it arrives here, let me call that as Y2. Now there's a closed end, no? And there's an open end. Now when a displacement, I'm discussing displacement wave. When a displacement wave reflected by a, let me use same color. By a closed end, it should undergo phase change of pi radian. So this will become Y3. Again, it will propagate and it will reach here. So what we have here, the tuning fork will be continuously vibrating. So it will be pushing it will be sending the disturbance into the pipe. So the disturbance or the displacement will propagate a length L, get reflected. Again, it will return back. Now, what is Y4? Y4 is the reflected wave, or you can further, okay, get reflected will become Wi-Fi. Then what is this? There's a twice, one more if you want, you take it one more. What is this Wi-Fi? Twice reflected wave, no? Once it is reflected at closed end, next it is reflected at the open end. Now, continuously the tuning fork will be sending signals. So shall we say there'll be interference between these two waves? Now, sir, why no phase change? Because we know when a displacement wave reflected by open end will not undergo phase change. When reflected at closed end will undergo phase change. Are you seeing that color? Inverted, I'm showing very clearly. This one. So now what will happen here? The fresh incoming wave and the twice reflected displacement wave. The fresh incoming displacement wave and twice reflected displacement will undergo superposition. Okay, that's one. So we can talk about the interference. Now, similarly, the fresh incoming wave and this Y4, they are moving opposite to each other. Now, the fresh incoming wave will be like this. And this Y4 is what? Like the reflected wave. They'll move opposite to each other. What is the condition for standing wave? Two waves of same speed, same frequency, moving opposite to each other, undergo superposition, will get a standing wave. So what all we see here? Interference. So there's nothing. So you can consider superposition of these two or these two. For standing wave, I'll consider these two. Fresh incoming wave and the Y4. For interference, I'll consider these two here. So of course, just get reflected, phase change off, no phase change will come. So there won't be much difference here. So got the idea, no? So like this, what happen? I'll take the superposition of the different waves here. So in interference phenomena, the reflection is occurring and also a standing wave pattern is also obtained. Okay, let's calculate the condition for what is my question is I have to derive the resonant frequencies of the pipe, no? What do you mean by resonant frequencies? Why resonant frequencies will come here? Why that idea? So let me take superposition of the fresh incoming wave and the twice reflected displacement wave. What is the phase difference between them? Let us consider the superposition of fresh incoming displacement wave generated by tuning fork and reflected wave. Let me just write reflected wave y4. Superposition of these two. So because of this, what happened is standing wave is obtained. Then what is the overall phase difference? So let's go for the phase difference. What is the phase difference now? Phase difference due to reflection, phase difference due to path. Compared to the fresh incoming wave, how much of path length this will cover extra path? It will cover a distance L, then again L2L it will cover no. So definitely it will gain some phase. So can you remember yesterday's class, like if a wave propagates some distance, it will gain path. So if a wave propagates some distance, it will gain phase. So definitely the fresh incoming wave and the Y4, will there be any phase change? Yes, there'll be phase change. There'll be phase change. They will have a phase difference. Due to what? Due to path. And also it got reflected. So therefore I'm reflecting, I'm adding both here. Now due to reflection, how much of phase change? Pi radian. Due to path, how much it should be? Due to path, so 2 pi by lambda into 2L. Are you able to understand? So why this 2L? Because it has covered additional path, no? L plus L, this is 2L. Okay, now again, why do we play musical instrument? To get a maximum sound, no? So therefore, what shall I go for this? Shall we go for constructive or destructive interference of the fresh incoming wave, or Y4 or Wi-Fi? I should go for constructive interference. So we do play musical instruments to get the maximum sound. To get a maximum sound, what happened? I should design musical instrument where the constructive interference will occur of the waves. For that purpose, what should be this phase difference? Should be equal to 2n minus 1 pi or 2n pi. What do you suggest? Because you know enough of some mathematics. Yesterday we discussed no the interference that is only you have to bring that one. So 2n minus pi or 2n plus pi. Why no answers? There's a very simple topic, no? You know most of the things. So construct, actually we have discussed now the interference that only has to be explained, that only has to be applied. For constructive interference, what should be the phase difference? Yesterday's idea, I want you to think 2n pi, no? For constructive, for destructive interference, 2n minus 1 pi. Am I right? Yeah, good. Yeah, 2n pi, it should be that one. Huh? Just recollect why 2n pi. For constructive. Next, you can say, okay, sir, why constructive interference? For constructive interference or to get maximum sound. This is a basic idea, that one. So now this will become how much it is. This will be 2n minus 1 pi equal to 4 pi L by lambda. Or this will become 2n minus 1 equal to 4L by lambda. Okay, I'm at a better position now. What is lambda? Lambda, I'll write it as V by F. So what are the expression for resonant frequency? 4L F equal to 2n minus 1 V by 4L. What are the possible values of n? Okay, let's go for resonant frequency. I'm using word resonance. Recollect the standing waves. So the first one, the first, the same pipe. I to show the both the things. No, pressure wave, displacement wave. What should be the put n equal to 1? So what are the values? N equal to 1, 2, 3, it will start. N equal to 1, 2, 3, 4, 5, 6 like this. Put n equal to 1. So what is the length of the pipe? So first we'll go for put n equal to 1. It will become lambda 1. So let me derive let me write this equation. L is equal to 2n minus 1 lambda by 4. Will I agree? Put n equal to 1. What do you get? Lambda 1 by 4, the first one. So first n equal to 1. Fundamental tone or first harmonic. So if you put n equal to 1, what is the length? L1 will become the length of the pipe. I will write it here. So then I'll magnify it. Now you see this. Let me come to the here. Please all of you look at here. Put for n equal to 1, how much it will become? The length will become lambda 1 by 4. So we know this should be the displacement node yn, I'll write it. And open end will be displacement antinode. Then the length of the pipe equal to lambda 1 by 4. So what do we should get? We should get off loop. You are going to get a only off loop. Length of the pipe is L lambda 1 by 4. Similarly, so we know this end. What is the this end? This should be the pressure antinode, and the open end should be a pressure node. So how the standing wave? The standing wave should be pressure standing wave should be like this. Why sir? Why you are going for off loop? Why not you go for full loop? So what is the length is equal to? Lambda 1 by 4. So this called like a fundamental tone or first harmonic. So this is what I'm showing. The displacement the displacement standing wave set up in the organ pipe, or the pressure standing wave set up in the organ pipe. And strictly this is a closed end, this is open end. We're discussing for this one. Okay, now similarly for next n equal to 2. N equal to 2, it is called as a first O tone third harmonic. So what is the length of the pipe equal to 2 into 2 minus 1 lambda by 4. How much we are getting? 3 lambda 2 by 4. 3 lambda 2 by 4 means what you can write? Lambda 2 by 4 plus lambda 2 by 2. So now what we'll get it? We'll have the same pipe, no? Now what's be the diagram? The displacement node. So one full loop, sorry, one off loop. So this should be the pressure, displacement node, antinode, displacement node, and the length of the pipe is L. Pressure node, pressure antinode, pressure node, pressure antinode. Now, why third harmonic? Now, if you, okay, sir, you're not writing resonant frequency. Let's write equation for resonant frequency. Put n equal to 1, so V by 4L. So what is the first resonant frequency? F1 will be, I'll write in black color. Please do remember, these are very important. Then what is F2? No. Why we are calling it as third harmonic? You can see like a first, third, like this we got it. V by 4L, 3V by 4L. What is V? Speed of the sound in the organ pipe. It depends upon the medium here, temperature, all other things like sound wave propagation, what we had. Okay, similarly, we'll go for n equal to 3. Yeah. N equal to 3. So this is called like a second overtone. Or fifth harmonic. Then what is L is equal to length of the pipe will be 2 into 3 minus 1 lambda by lambda 3 by 4. Or this will become how much? It will be 5 lambda 3 by 4. No, 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 no. Don't call fourth harmonic n equal to 3. So we should call it as a fifth harmonic. The odd harmonic, the even harmonics are absent, no? And what is F is equal to? F5. The symbols, if you are getting confusion, put n equal to 3, this will become F5. F5 will become 5V by 4L. F2, F3 we are written, no? Symbols will be confusion. If you want, you can write it this as n equal to first overtone or third harmonic. So this will become lambda 2 or lambda 3. Better let me write it as 3 this one. So that's, of course, n equal to 2, I should write lambda 2. Since even harmonics are absent, no, I'm changing symbol accordingly, so that will be in better position. Okay, how the standing wave pattern will be there in the pipe. Okay, this is the length of the pipe. No. So there's a pressure displacement node. So we should get two end of loop. There's a pressure antinode, pressure node. Okay, fine. So these are the resonant frequencies. Like this is what we are representing. This is called like a second overtone or fifth harmonic. The even harmonics are absent. Okay, just be careful the names what we give. Okay, this is about the resonant frequency. So you can say like who is the tuning fork? The tuning fork will change. Means like we are not understanding why you are using word resonance. Okay, let's come here. I think you can really understand things very clearly. The word resonance. Okay, I'm trying to discuss. Okay, let's take tuning fork. This one. So there's a closed end organ pipe. It's a fundamental frequency is say like a 100 hertz. I'll bring a tuning fork of frequency say 100. This is a tuning fork of frequency 100 hertz. What is F1? F1 is a fundamental tone or first harmonic. Anything, whatever you want. Fundamental tone or first harmonic. So what do we notice? We notice like a this is like a displacement wave. Let me take. So shall we go for off loop? Okay, then what do you mean by that? When the frequency of tuning fork becomes equal to 100 hertz, we'll get here the maximum transfer of energy takes place from the tuning fork to the organ pipe, and we do get maximum sound. Now, if I bring another tuning fork, this is very important. Please do all of you. There, the wire, it was a little bit difficult. Now this will be very clear. Now, if I bring another tuning fork whose frequency is 300 hertz, then the same pipe now is going to resonate such that 1.5 loop will be there. Are you getting now? The same pipe will vibrate in 1.5 loop. Now, if you bring 500 hertz, 500 hertz, then 2.5 loop will come. Sir, I'll bring 200 hertz. Tell me what will happen. This is what our discussion. What do you mean by resonance? We'll get an exact picture. Now, a student, what happened? Will strike the tuning fork to the rubber pad and will keep it. Okay, now this is let it be 200 hertz. What is the resonance frequency of this? 300 hertz. The value of the length of the pipe, all they are so adjusted that the resonance frequency is 100 hertz. That one means here first will 100 hertz tuning fork. I'll bring it. Then there'll be maximum transfer of energy will take place from tuning fork to the organ pipe. I'll get maximum sound. Then when I bring tuning fork of frequency 300 hertz, then it will resonate in 1.5 loop. Third harmonic, it will vibrate. Then maximum transfer of energy takes place from the tuning fork to the organ pipe. I'll get a maximum sound here also. So I should write maximum sound. Is produced. Maximum sound is produced. What will happen here? It will vibrate, but there won't be resonance and we don't get maximum sound. Hardly any sound is produced. The reason for that, no resonance. Here resonance occurs. So who will supply that energy? Who will supply that energy? The tuning fork. There'll be maximum flow of energy. So it'll be like this. Here also, what all the energy of the it is vibrating, no? It will give that energy to the organ pipe. So there'll be maximum transfer of energy from the tuning fork to the organ pipe. When the frequency of tuning fork becomes equal to resonant frequencies of the organ pipe. If you bring 200 hertz, the tuning fork will vibrate. Don't say tuning fork will not be. Tuning fork will be vibrating. It will push sound waves. Okay, that one. Yeah, the resonance will not occur. Sir, what about the frequency with which will vibrate? It will vibrate with 200 hertz only. Then what about like a standing wave? No, we hardly get any sound. So no question of designing equipment here. A good example, I think you might have played, no, the pen cap. You try to blow or say whistle. You can see my whistle, no. I'm blowing whistle. Some of you try, you don't get. The reason for that, you are not blowing air at a frequency equal to resonant frequency. Sir, how come the whistle? So here, what I do, I'll take my, I think I'll show video. Some of you, sir, how whistle everything. It's a very simple, no? How it is possible? I think different ways, other two finger, three finger, something. I know this technique. So I'll put my fingers on the tongue. I'll fold the tongue, then I'll blow the air. So I'm blowing air at a frequency, and my lips, the tongue will become an organ pipe. So there the resonance will occur, will get a maximum sound. If I try other method, not get. The reason for that, not at resonance. Now you see this one. How it is possible? From where that sound has come? Now I'm blowing air. So why I'm not getting sound? No resonance. You can take pen cap. I think some of you know that one in school you might have played. No, you take pen cap and blow air nearby it. No, sometimes you get maximum, sometimes you don't get maximum sound. I'm not getting the cap somewhere. It is lying. My kid have kept somewhere. Now you can try with that pen cap. If you blow, no, you get maximum sound. Sometimes if you blow, you don't get sound. The reason resonance here. So we are not bothered when it is not at resonance. That's all. I'll never design equipment where I'll play music, I'll play it and don't get sound. So it should not be designed here. So this is like, if you design like this, you call like a stupid. That one, you don't have any brain. You are not fit to become engineer. You should design an instrument where it should generate music, no? So if you bring 200 Hz, then definitely we don't get any sound here. Hardly any sound is produced or no resonance occurs. Simplest thing. Sir, tell me what will happen. Like, yes, this wave will go, get reflected. The incident and reflected will come. They'll undergo superposition. Standing wave will come, but hardly we get any sound. So it's of no use for us. Resonance occurs. At resonance, when resonance occurs, what will happen? We'll get a maximum sound. Maximum sound is produced here. So therefore, what all I should design instrument to get maximum sound only, I should design instrument. Getting some idea what I mean to say the resonant frequencies here. So here, what is the thing? The pipe length is remained fixed. Again, okay, don't think sir, you have changed the length of pipe. The length of the pipe is same. Okay, now you have a cap, no pen cap. You can blow air at different frequencies. Only when the frequency at which you are blowing air, if it is proportional to resonant frequencies of that cap, you get a sound. If you want, you can try. If you want, you can try. This what we are discussing theoretically. This idea. If you want, you can try. No problem. I'll not object. Huh? Anybody can produce with a pen cap sound. Yes, anybody? Try it. No, let me hear. What, you don't want to become engineer? You should try all these things. No, why shy? All of you sleeping or they're in class? What you should do? See how to. Somebody is asking, sir, what to do that one. I think you might have played in school. No, if there's a cap, you blow like this. No, I think you used to disturb the classes. You have to take pen cap. You blow air like this. Huh? Just anybody try it. Unmute, and just let me hear it so that I'll come to that as you're really thinking and trying.
Sir.
Yeah. Sound should come. No, you're blowing air, but I want sound. Huh? I think somebody. Okay, it's not possible. Cap is not good. Okay, please. Others. Anybody try it? Huh? Okay, I'll go for next one. Okay, let me finish off open end organ pipe. Huh? Okay, this is what I wanted to discuss. Nothing big. Huh? Nothing very big idea. The small. Or what do you mean by organ pipes? Are it will produce a sound. That's all. Only when the frequency of tuning fork becomes equal to resonant frequencies of the organ pipe, we'll get a maximum sound. Okay, now we'll go for resonant frequencies of open end organ pipe.